Jai Hind everyone. This is once again Jyoti Sharma in front of you, giving you the lecture series on the topic electrical machines, which is unit 4 of the subject basic electrical engineering. The subject is having the code of KEE 101 and also 201 according to AKTU. In the series of the lecture related with this electrical machines, till now we have gone for 7 of the lectures, and in these lectures we have gone for various AC and DC machines, right? We have discussed their advantages, their applications, their constructions. The last machine what we have discussed in 7th lecture, that was a synchronous generator or alternator. So we have discussed its construction, the stator, the rotor. We have seen that in case of synchronous machines, the stator used to be the armature part and the rotor is formed by the field, right, which is just to the opposition of the DC machine. The construction is very much simpler. Once again, in the rotor construction, we would be finding 2 types of constructions. It can be either the salient pole type or the projecting poles type, right, which is generally being considered for low speed applications, whereas for higher speed applications, for if at all in case of generators, for the turbines having of higher speeds, likewise of turbo alternators, which we call it as, there it used to be a cylindrical rotor, right. There the poles are not projecting, but the unslotted portion of the core that used to form the pole part, right. Now coming to the 8th lecture, which would be the last lecture regarding this electrical machines, it is related with the synchronous motor, right. Construction will be discussing, the principle of operation for the synchronous motor will be discussing. While discussing the principle of operation, we'll be seeing that a 3-phase synchronous motor is not self-starting, right. The another machine what we have discussed earlier is also not self-starting, that is single-phase induction motor, right. Here also a 3-phase synchronous motor is not self-starting. So what will be the methods of starting it and what are its application? Moving on to the introduction regarding what is a synchronous motor, right. It is an AC motor in which at steady state, the rotation of the shaft is in sync with the frequency of the applied current, right. This is a motor, the input has to be an 3-phase AC supply and the output would be mechanical, right. So the synchronous motor works as an AC motor, but here the total number of rotations made by the shaft is equal to the integer multiple of the frequency of the applied current, right. So the synchronous motor doesn't rely on induction current for the working, right. So in these motor, unlike the induction motor, the multiphase electromagnets are present on the stator, that is what we have discussed, which produces a rotating magnetic field. Here, the rotor is of permanent magnet which gets synced with the rotating magnetic field, and then the rotor that rotates with the synchronous speed or in synchronous with the frequency of the current applied to it. That is why this term synchronous motor is being selected for this machine, as the speed of the rotor of the motor is same as that of the rotating magnetic field, which is nothing but the synchronous speed given by 120 F by P, where F is the frequency of the input supply, right, and P is the number of poles on the rotor. Now, going with the construction, if at all I say. So, the construction of the synchronous motor is as shown, which is being given. So, just like any other motor, it consists of stator, rotor. The stator core is constructed with a thin silicon laminations and insulated by a surface coating. We know the very reason why it is being laminated, to reduce the eddy current losses, right? And the stator core is constructed with silicon because to reduce the hysteresis losses, right? So, the stator has eggshell slot insides in which the 3-phase stator winding is placed, right. So, the stator is wound with a 3-phase winding for a specific number of poles equal to that of the rotor poles, right? And generally, the winding for the stator is used to be of star type, right? The rotor in the synchronous motor is mostly of the salient pole type, although when we have gone for the construction, we have seen that the rotor can be with two constructions. It can be either salient type or it can be either cylindrical. But in case of synchronous motor, mostly the synchronous motor are having a salient pole type construction. So the DC supply is given to the rotor winding via slip rings, right? So this direct current excites the rotor winding and creates the electromagnetic poles. In some cases, the permanent magnets are also being used, right? So the figure which is being shown over here, that gives the construction. Now for the motor, if at all we just see, in this case we used to give a 3-phase AC supply to the stator. The 3-phase AC supply is being given to the stator, as well as the DC supply is also being given to the rotor, right, for forming the poles, right. So in this case, 3-phase synchronous motor is being called as doubly excited motor or doubly excited system, right, as the stator is also being excited with 3-phase AC supply and the rotor is also being excited with the help of DC supply, 220 volts, right. Now, what is the working principle of the synchronous motor, right? How does this motor works? If both of the supplies are being given, then how there would be the rotation of the rotor which will be achieved? So, the working principle for a synchronous motor, it works on the principle of magnetic locking, right? And what do we understand with magnetic locking? This is so simple to understand, whenever, two unlike poles are brought near to each other, if the magnets are strong, there exists a tremendous force of attraction between these two poles. In such condition, the two magnets are said to be magnetically locked, right? These are said to be magnetically locked. And now, if at all one of the magnets is being rotated, then obviously the other also rotates in the same direction with the same speed due to the force of attraction, right? This is being called as magnetic locking condition, right, which is being shown in the figure. Now, so to have the magnetic locking condition, there must exist two unlike poles and magnetic axis of the two must be brought very close to each other so that there is a strong magnetic force of attraction between the two, right. So, let's see the same principle being applied to the synchronous motor, then how the motor is going to work. Right. Now, if it is just consider a 3-phase synchronous motor whose stator is wound for just 2 poles, right, then the 2 magnetic fields are produced in the synchronous motor by exciting both the windings, stator and rotor, stator with the 3-phase AC supply and rotor with the DC supply. When the 3-phase winding is excited with the 3-phase AC supply, then the flux produced by the 3-phase winding is always in the rotating type. We have seen in case of 3-phase induction motor that when you provide a 3-phase supply to the stator, there would be a production of rotating magnetic field which rotates in the space. In this case now, the stator is wound for just say 2 poles, say for 50 Hertz. So, the speed of the rotating magnetic field would be how much? 120 F by P NS. So, 120 into 50 divided by P2. So, that is going to be the highest synchronous speed, 3000 RPM. So, this effect is very much similar to the physical rotation of the 2 poles with the speed of NS, right. So, now the direction obviously, now the direction of the rotation of the rotating magnetic field, say I am just considering it as clockwise, right. So, when the field winding on the rotor, now it is being excited with the DC supply, it also produces 2 poles, assuming the rotor construction to be of 2 poles, salient type, right. If at all I just say that N1 and S1, if at all I just say that this is the stator, when we give a 3-phase supply to the stator, there is a production of rotating magnetic field, right, and it produces 2 poles N1 and S1 in the stator, okay, and the direction of this is, say, clockwise, ns, rotating with the speed of ns. Say for 2 poles, it has to be 3000 rpm. We have seen, right? Now, at the rotor, that is also salient type, it is also being made for 2 poles. So, if at all I just say that this is the rotor, salient pole type. Now, in this case, when you give the DC excitation, now once again the poles would be formed. Supposingly the poles formed in this case is, say, S south over here and north over here. This is 2, N2 and S2. This is south, S2, and this is N2. Now, what is happening in particularly this case? I am having both the poles being created, right? In the stator, I am having north and south. In the rotor also, I am having south and north. In this case, what is happening now? These 2 poles are oppositely charged. This is north, this is south, this is north, this is south. So, there will be, as both of these are unlike poles, there will be a strong magnetic force of attraction between these 2 and these 2. Their magnetic axis would be aligned. So, when there is a magnetic axis which is being aligned, and we also know that this is actually a rotating magnetic field at the stator, which is going to rotate with the speed of ns. So, what will happen? So, this rotating magnetic field will get the rotor into synchronism and will make the rotor also to rotate with the same speed as that of the rotating magnetic field of the stator. That's why, because of the magnetic locking which has been happened, this rotor will also rotate in the same direction and also with the same speed as that of the rotating magnetic field, which is having the speed of synchronous speed, right? That's why the motor, the synchronous motor, will also be running at synchronous speed. Does this happen so easily? Is it so necessarily that the poles would be exactly aligned? Is it practically so feasible? Can't it be like that the south pole they are opposite, but exactly the magnetic axes are not being aligned? It may be either towards right side or left side. Then at that instant, what is going to happen? Right? So, we'll be seeing that exactly this kind of force of attraction, does it really makes the motor to get started? Right? This is not practically every time possible. Right? So, there is no practical magnetic locking taking place initially. That's why the 3-phase synchronous motor are not self-starting. But the principle of working is this: the motor is going to work like this only. That means there has to be an existence of a magnetic locking between the two, between the stator poles and the rotor poles. To make that magnetic locking being occur to happen, we have to do certain managements. So, first we'll be seeing what would be happening if these are not exactly aligned, right? And these are, the rotor is exactly is shifted by a right side or left side. So, why this is not self-starting? Synchronous motor, why it is not self-starting, right? Now, consider, consider the rotating magnetic field is equivalent to the physical rotation of the 2 stator poles, right? One is north and south. Here you can be seeing this is the stator poles, right? This is north, this is south. Now, consider an instant when the 2 poles are in such a position where the stator magnetic field is vertical, right? And say rotor poles are arbitrarily positioned, right? At this instant, the rotor is stationary and unlike poles will try to attract each other. Say, if at all I say that this is figure A, in this figure A, if at all I just see, right? the north pole is over here for the stator and the south pole for the rotor is over here. So what is going to happen? The opposite poles are going to get attracted, right? Or I may say the common poles will be having a force of repulsion, right? So because of the force of attraction between the opposite poles, the rotor will try to rotate in anti-clockwise direction, right? There will be a force of attraction which will drag this rotor towards itself, right? But while the motor just tries to do that, what will happen? Because this is not a permanent pole which has been created. This is not a DC supply being given. This is an AC supply being given to the stator. So what is going to happen? It is having a frequency of 50 Hertz. So at the very next instant, the poles would be changed, right? Now this time at the stator, I'll be having south pole, right? And the rotor will be having north pole, right? The placement is the same because the rotor hasn't moved till now, right? Okay, but the poles of the stator has changed. Now what will happen? Now you can see here it is south and here it is north. So there will be a force of attraction between this south and this north. So the rotor will try to rotate in which direction? It will try to rotate in clockwise direction. Once again, the rotor will think of it, and when it is just trying to rotate, the very next instant, right, once again, I'll be having instant A. Once again, the stator poles are going to get reversed. Here I'll be having north, here I'll be having south. Once again, the force of attraction, because of that, once again, anti-clockwise torque, then clockwise torque. So what the rotor is going to do now? Because the rotor is having a high inertia, it will never be rotating neither in clockwise, neither in anti-clockwise. It will be at standstill condition. It will not be starting at all, right? That's why a three-phase synchronous motor is not self-starting. We have seen because of this condition, it is not self-starting, right? I'm not getting a unidirectional torque in which I'm not getting the magnetic locking being done, which is actually the working principle of a three-phase synchronous motor. Because of that, because the magnetic locking is not being done, I'm not getting a unidirectional torque being generated in any of the direction, neither in clockwise, neither in anti-clockwise. How to make this happen now? Right, we'll be seeing that in the various starting methods of it. Okay, there may be a question that, okay, we have seen when the rotor is being shifted slightly towards the left side and if it is shifted towards the right side, right? So exactly the magnetic axes are not being aligned. So there may be a case, what we have discussed in the principle, that I may be having this case as well, right? That I'm having stator poles like this and the rotor poles like this. The axes are also being aligned, north and south. So in this case, you may be saying, yeah, the magnetic axes are being aligned, but once again, the inertia, the high inertia of the rotor doesn't allow, because it is not having any initial torque, right? The rotor is not rotating in any of the direction. So just by having the force of attraction of it, you know, the rotor, because of its high initial inertia of the rotor doesn't rotate neither in clockwise direction or in anti-clockwise direction. So all the three cases fails. That's why a three-phase synchronous motor is not at all a self-starting motor. Okay, so how to get it started? Right? How to get that starting torque? So there are various methods by which we can be making the synchronous motor self-starting, getting it started. The very basic thing what we get from all the thing what we have discussed earlier is, if at all by certain means I make the rotor to rotate with a speed which is slightly closer to the synchronous speed or the speed of the rotating magnetic field, and then I give the excitation. So there are many likely the chances that there will be a force of attraction, there will be a magnetic locking between the stator and the rotor poles, and as the rotor is rotating, right, it's not at standstill condition, it is having a very low inertia now. It is rotating actually. Right. So at this position, when the magnetic locking happens, what will happen? It will drag the rotor into synchronism and make the rotor to rotate with the speed of synchronous speed. Right? And that is what we want. So according to that, the starting methods, the very first starting method, that is by using pony motors. As the name is suggesting, the pony motors are like small induction motors. We can start the synchronous motor with these. These small induction motors are being coupled to the rotor of the synchronous motor. The function of the induction motor is to bring the rotor closer to the synchronous speed of the motor. Right? It's not exactly equal to it, but near to that, right? Once the rotor attains the synchronous speed of the pony motor, once it is rotating at a sub-synchronous speed, right? There will be giving a DC excitation. Till then, the DC excitation will not be given, right? So when we give the DC excitation through the slip rings, what is going to happen? There will be a magnetic locking between the stator and rotor poles, right? And the rotor will be dragged into synchronism and the rotor will continuously rotate with the synchronous speed or as the speed of the stator magnetic field, right? And that is what we want. Now the pony motor is not at all required. Once the motor has achieved its speed, right? Now, because I only require the starting torque, right? Now the pony motor can be decoupled from the rotor, right? That is the very first method, that is by using small induction motors or AC motors being coupled to the rotor. Another can be the same thing. The another can be by using DC machines, right? There is an advantage with the DC machine. What is that? Many times these large synchronous motors are provided with a coupled DC machine, right? This DC machine is used as a DC motor to rotate the synchronous motor at a asynchronous speed or sub-synchronous speed, which is slightly lesser than the synchronous speed of the rotating magnetic field. Now, when the excitation is given to the rotor, now once the motor starts running with the synchronous motor once again, once the poles are being created, magnetic locking would be there and now the motor will start to rotate at the synchronous motor. The same procedure what we have seen with the pony motors. But now, the same machine, the same DC machine which was acting as a DC motor to make the rotor to rotate at subsynchronous speed will now act as DC generator. For what? It will be called as exciter to give the field excitation to the synchronous motor, right? So, the same DC machine can be work as an exciter, that is being called as motor generator set, right? So, it can be working as an exciter itself. So, that is an advantage by using a small DC machine being initially will work out as a motor to start a synchronous motor and later on it will be working as an exciter to give the DC supply to the field excitation. Now, the most common kind of starting which is being done is by using damper winding. This is a third kind of starting method, right? Now, when a three-phase supply is being given to the synchronous motor, we have seen that it fails to start, right? Now, in order to make it start, there would be a small modification being done in the construction, that the copper bars are circulated at both the ends of the rotor, right? So, to the rotor construction, it can be seen, this is the rotor construction, right? It is a salient pole construction. In this, the copper bars are inserted. Here you can see these are the field windings being given for the field excitation. And at the pole shoes, you can see, the copper bars are being inserted. These, I'm talking about these. The copper bars are being inserted, right, and are placed on the rotor. These bars and the windings are being called as damper windings. And these damper windings, these used to be short-circuited windings and used to be short-circuited with the help of end rings only, right? So the construction is now very much similar to that of a squirrel cage induction motor, right? In three-phase squirrel cage induction motor, we have seen that, you know, the rotor circuit is used to be short-circuited with the help of copper bars or aluminum bars, and they used to be short-circuited with the help of end rings. The same kind of construction is being given in case of damper winding, right? So we used to have two windings in it. One is the main field winding, and another one is the damper winding, which is being provided at the rotor circuit, and this is a short-circuited winding which is being given, right? Or it is very much similar to a squirrel cage. Now, what used to happen? When the supply is being given to the field winding, it starts up a rotating magnetic field. You know, when the three-phase AC supply is being given to the stator, the rotating magnetic field is being set up, right? Now, because of the damper winding is being used, which is acting, which is making the construction very much similar to a three-phase squirrel cage induction motor. So, what is going to be done, right? I'm having a rotating magnetic field, I'm having a short-circuited rotor. The rotor conductors will experience flux cut, right? Because of the flux cut, I'll be having an induced EMF. These are short-circuited, will be having current. Current carrying conductor placed in the magnetic field will experience torque. Once again, the torque would be, or the induced EMF would be in such a direction so as to reduce the relative motion. So the rotor will start to rotate in the same direction as that of the rotating magnetic field, but will it be achieving the same speed? No. It will be running with a sub-synchronous speed or with a asynchronous speed, which is slightly lesser than rotating magnetic field. That means the complete process, what I repeated, is nothing but the starting of three-phase induction motor. So, although it's a synchronous motor, but because of the damper winding, the machine will now, or the motor will now start like a three-phase squirrel cage induction motor with a speed slightly lesser than rotating magnetic field. That is what we want, right? Now, once the rotor is rotating with a subsynchronous speed, which is slightly lesser than rotating magnetic field, now the DC excitation with the main field windings would be given. The DC excitation would be given, right? Now, when you give the DC excitation, what has happened? The permanent poles would be formed in the rotor circuit. Now, when the permanent poles are being formed, once again, at the very next instant, I'll be having a magnetic locking being done between the stator and the rotor poles. Once the magnetic locking is being done, now the motor or the rotating magnetic field will drag the rotor into synchronism and will make the rotor to rotate with the speed of ns, or rotating magnetic field. That is how the damper windings helps in making the three-phase synchronous motor being self-starting, right? But the disadvantage with this kind of starting is actually because of the rotor copper bars. You know, the rotor circuit is having a high copper loss. Because of that, the efficiency is comparatively lesser, right? That is one of the disadvantage with it. Now, once the motor starts to rotate, right, what will be happening to the damper winding, right? It will still be producing its own torque, or will it be producing its own EMF? No, if you just see, as in case of three-phase induction motor, once the motor starts to rotate at a speed of ns, there will not be any relative motion between the rotating magnetic field and the rotor. If there is no relative speed between the rotating magnetic field and the rotor, there will not be any induced EMF in damper winding, right? There will not be any induced EMF, it will not be having any current, no flux cut, no current, no torque being produced. So, it will be sitting like that, right? So, it will be just out of the circuit. It will be there, but it will be out of the electrical circuit, right? So, that is the functioning of the damper winding. The last kind is, as the last starting method is as slip ring induction motor, right? which we always call it as a synchronous induction motor also. In this case, now this, if at all we just go with the circuit, in this method, an external rheostat is connected to the rotor through slip rings, right? Here, the ends of the damper windings are brought off the motor and connected either in star or in delta, right? This is, if you just see, this circuit is very much similar to that of a slippering induction motor or wound rotor, right? The rotor, the terminals are being brought out, right, with the help of slip rings and brush assembly, right, and a DP-DT switch, dual pole, dual throat switch, One side we can be connecting it with the starting resistances, likewise we used to do in slippering induction motors, and towards the another side will be providing the DC supply, right? The two terminals being short circuited and then, being given the DC supply. Now what will be happening at the very initial, right? The contacts will be made towards this side, towards the starting resistance side. So at this very instant, so when I give the AC supply to the stator, the rotating magnetic field would be formed and the rotor conductors would be excited, obviously will be producing the EMF, the torque. The rotor will, depending upon the starting resistance, obviously the current would be limited and the starting torque would be comparatively large. We have seen that, right? If the starting resistance is more, so the starting torque can be produced, more starting torque can be produced. So this is actually the working of the three-phase squirrel cage induction, the three-phase slip ring induction motor. Likewise, that it will start with the speed of ns, no, with the speed of nr, which is slightly lesser than ns, and that is what we want. Now the rotor of the synchronous motor is running at a speed which is slightly lesser than ns, and that is what we want. Now once it takes up that speed, now the switch would be given towards the DC supply. When the DC supply is being given to now the stator conductors, right, at that instant, now once again the permanent poles would be formed, magnetic locking would be happening, and now once again the rotor would be pulled into synchronism and now the rotor will rotate at a speed of ns. So basically in this method we are making the synchronous motor to initially start like a slip ring induction motor, right, with a speed lesser than ns, and then it will be rotating at synchronous speed. So these are the four methods by which this starting of three-phase synchronous motor is being done. Coming to the applications of synchronous motor, it is finding its application in wide range. The very first one is power factor correction. An overexcited synchronous motor works on a synchronous condenser as a synchronous condenser and used for the improvement of power factor of industrial loads having lagging power factors, right? An overexcited synchronous motor is actually, the synchronous motor is having a function that it may be working for a leading power factor or lagging power factor or unity power factor, right? So when an overexcited synchronous motor is being made to work, that means the excitation being given in such a way that the induced EMF is greater than the supply voltage. In that case, it is being called as overexcited synchronous motor. At that state, it will be acting, it will be giving us the leading power factor. It will be working like a synchronous condenser. And that can be given for the improvement of power factor for a heavy industrial loads, right? The second application would be for a constant speed applications, because the synchronous motor that used to work with a constant speed of ns, right? So the synchronous motor that provides a constant speed at high efficiency, so they can be used for constant speed applications such as centrifugal pumps, fans, blowers, shafts, motor generator sets, synchronous clocks, air compressors, paper mills, cement mills, etc. The third one is they can be used for improving the voltage regulation of the long transmission line. A synchronous motor, it acts as a field regulator. It can be used to control the voltage at the end of the long transmission line by varying its excitation. Last one, that is, it can be used as frequency changer. A synchronous motor can be used to drive another alternator to generate supply at different frequencies due to its constant speed nature. In this case, it is being called as frequency changer. So these are the various applications. So till now we have discussed mainly the kinds of AC and DC generators and motors being discussed in the last unit, electrical machines, according to AKTU. Thank you all for listening me so patiently. Thank you.